Welcome to the Deep Dive. We're the show that wades through, piles of research, articles, notes, all that stuff to pull out the key insights for you.
Yeah, cutting through the noise.
Exactly. And today, we're tackling artificial intelligence.
Uh,
It often feels like, magic, doesn't it?
yeah,
Pure sci-fi stuff.
it really can seem that way.
But underneath, it's actually built on some surprisingly logical, mathematical ideas. So today's deep dive is the math behind the magic, probability, patterns, and predictions.
Hmm.
Our mission really is to demystify how AI actually thinks, or, processes information and makes decisions. We want to reveal the math that's powering it all.
That's the plan. And for this, we've dug into some pretty foundational, sometimes quite dense material. We're mainly drawing from the 100-page machine learning book by Andrei Burkhoff.
The classic.
Definitely. And we're adding insights from Martin Ford's Architects of Intelligence, plus some strategic thinking from Andrew Dang's Machine Learning Yearning.
Good sources.
The goal here is to pull out those core mathematical ideas that make AI tick, give you a shortcut to understanding the, let's call it math magic, without getting totally lost in the weeds, in the jargon.
Like getting an insider peek at how these systems really work.
Exactly.
Okay, so let's jump right in. We feed AI all this information, text, images, numbers, whatever. How does it even start to make sense of it? How does a computer even begin to understand? It feels like a black box.
It does, but it's not. The very first step is something called representation. AI needs information structured, and fundamentally it needs it as numbers.
Numbers, okay.
Think of it like teaching a computer to see the world as measurable features. We use something called a feature vector. It's basically just a list of numbers describing, anything.
So like if it's looking at a house.
Yeah, exactly. The feature vector might have numbers for square footage, number of bedrooms, maybe the year it was built, simple numbers.
But what about things that aren't numbers, like colors, red, yellow, green?
Good question. Our sources talk about a neat trick called one-hot encoding. It's a way to turn those categories into numbers. So red might become, say, a vector like a 100.
Oh, I see, like a switch.
Kind of. Yellow could be 0110, green 01011. So each category gets its own unique numerical code. It's a clever way to represent non-numeric features so the machine can process them mathematically.
Okay, that makes sense.
Yeah.
So numbers are the ingredients. What then, once it has these feature vectors, what can it actually do with them to find patterns? It needs some basic math tools, right? A vocabulary.
Absolutely. And the vocabulary is built on surprisingly simple math operations, things you probably learned way back, like the idea of sets, just collections of things, or in this case, data points.
Yes.
AI can perform basic operations on them, like union, which is just combining two sets. If you have 1, 3, 5, 8, and 1, 8, 4, their union is 1, 3, 4, 5, everything combined.
Good.
Or intersection, which finds what they have in common. For their same sets, the intersection is just 1, 8. This is how AI starts to see relationships, commonalities, differences in data.
Simple operations, but powerful when applied to massive data sets, I imagine.
Exactly. And when it needs to add up lots of values, like all the numbers in a feature vector or maybe the errors it made across many attempts,
Yeah.
it uses capital sigma notation. It looks a bit intimidating maybe, but it's just a compact way of saying add all these things up. Super useful for summing over collections or vector parts.
So just efficient addition.
Pretty much.
Wow.
And another basic concept is the assignment operator, like a fx. It just means a variable a gets a new value based on some calculation fx. This is fundamental to how AI updates its knowledge or parameters as it learns.
Right, changing its internal state.
Precisely. These simple tools, sets, sums, assignments, they're the building blocks.
Okay, so we have the building blocks, representing things as numbers, doing basic math like comparing sets or adding things up. How does AI use this to actually find patterns and make predictions? This is where it gets really interesting, right? How does it learn spam from not spam? Or predict health outcomes?
Yeah, this is where the learning happens. The core idea here is often a supervised learning algorithm,
Supervised, meaning?
meaning you give it a data set that already has labels. So for spam, you'd give it millions of emails, and each one is already marked spam or not spam.
The training data has the answers.
Exactly. The algorithm uses this labeled data to build a model. The model's job is then to take a new email, one it hasn't seen, turn it into that feature vector we talked about.
The list of numbers.
Right. And then output information that helps it decide on a label, spam or not spam.
Does it just say yes or no?
Often it's more nuanced. Many models, especially for classification, output a probability, like a score between 0 and 1.
A probability. So not just black and white.
Correct. It might say, okay, based on its features, there's an 85% probability this email is spam. Or maybe there's a 0.85 score, which you can interpret as confidence or likelihood.
That seems much more useful. A degree of certainty.
It is. It gives you a spectrum, not just a hard yes/no. Very valuable in practice.
Okay, so sticking with spam, how does a model like, say, a support vector machine in SVM use this probability idea or make the actual decision?
Right. SVMs are a classic example. So the email becomes a feature vector. Then the SVM does a specific calculation. It essentially multiplies that vector by some learned values. Let's call them W for weights.
Right, okay.
Subtracts another learned value, B for bias, and that looks at the sign of the result. Positive might mean spam. Negative might mean not spam.
But where do W and B come from? That feels like the magic part.
Yeah, that's the core of the learning. The machine finds the best W and B by solving an optimization problem. This is something computers are really, really good at, finding the optimal values for a function, often under certain rules or constraints.
Optimization. Finding the best possible answer.
Exactly. For an SVM, the optimization goal is to find the highest margin between the classes. Imagine plotting all your emails in some high-dimensional space. The SVM tries to draw two parallel lines, or hyperplanes.
Hyperplanes, like flat surfaces in higher dimensions.
Precisely. It finds two hyperplanes that separate the spam from the not spam with the widest possible gap or margin between them. The wider the margin, the better.
Why is wider better?
A wider margin generally means the separation is more robust, less likely to misclassify things that are close to the boundary. Interestingly, this margin width is related to something called the norm of W.
Norm. Like a size measure.
Sort of, yeah. Don't worry too much about the term norm. Just know that a smaller norm of W corresponds to a larger margin between those separating hyperplanes.
Okay. So smaller W norm means a bigger, clearer gap between spam and not spam. It's finding the cleanest dividing line.
You got it. That's the geometric intuition. This clear decision boundary is how it classifies new emails. And it's these kinds of mathematical rules and boundaries found through optimization that let AI do complex things like recognize images or translate languages, even if you never see the math yourself.
Amazing. It's like defining territories in data space. So, okay, it finds these boundaries, but you said it learns. How do these models actually get better over time? It can't just set W and B once, right?
No, definitely not. It's about continuous improvement, and that brings us back to optimization. To improve, the model needs to know how to adjust its parameters, like W and B.
How does it know which way to adjust them?
That's where calculus comes in, specifically concepts like derivatives and gradients. The gradient, in simple terms, points in the direction where a function increases the fastest. In machine learning, we often want to minimize error, so we look at the negative gradient.
So the gradient tells it the direction of steepest change.
Exactly. It shows the model which way to nudge its parameters, W and B, to reduce the mistakes it's making, or in some cases, to maximize the likelihood of the training data being correct, which is common in models like logistic regression.
Okay, and how does it use that gradient information?
A very common technique is gradient descent. It's quite intuitive, actually. Imagine you're blindfolded on a hilly terrain trying to find the lowest point.
Okay.
You can feel the slope right where you're standing. What do? You take a small step downhill in the direction of the steepest slope.
Right, follow the downward slope.
Then you stop, feel the slope again at your new position, and take another small step downhill. You repeat this iteratively.
So small steps, constantly reevaluating the slope.
Precisely. As one of our sources puts it, talking about a related method, the gradient showed the direction, but we didn't know how far we should go. So we used a small step at each iteration and then reevaluated our direction. This step-by-step adjustment, guided by the gradient, is how the model learns. It keeps tweaking W and B until it finds values that minimize the error.
That's the descent part, going downhill towards the lowest error.
Exactly. This iterative refinement is why AI seems to improve itself by processing more data. It's constantly optimizing its internal parameters based on feedback.
So what does this learning process mean for us, the users? Why does a model trained this way work on new stuff it hasn't seen before?
That's the crucial part: generalization. If the algorithm, through optimization like gradient descent, finds a really good, robust decision boundary, that wide margin we talked about in the training data,
Yeah.
then new unseen examples that naturally belong to one class or the other are likely to fall on the correct side of that boundary too. They fit into the subspaces the model learned to separate.
So it's learn the underlying pattern, not just memorize the training examples.
Ideally, yes. That's the goal. When it works well, the model generalizes, making accurate predictions on data it's never encountered. This is why AI is so powerful for prediction tasks.
Okay, that makes sense. Now let's push this a bit further. We've talked about categories like spam, but how does AI handle really complex patterns, like understanding human language nuances or playing incredibly complex games like Go? That seems like a huge jump.
It does feel like a leap, but surprisingly, it often builds on these same ideas. Numerical representation, finding patterns, optimization just scaled up massively and with more complex models, like neural networks.
Neural nets,
Yeah.
inspired by the brain.
Inspired, yes, but as experts like Yoshua Bengio point out, they're not direct copies of how the brain works. Think of them more as complicated circuits with many layers of interconnected nodes or neurons.
Layers of calculations.
Right. And a key ingredient that lets them learn complex, nonlinear patterns that aren't just straight lines, is the use of nonlinearities. These come from activation functions within the network.
Activation functions, what do they do?
They're like little mathematical switches or transformations applied at each node. They take the combined input signal and transform it in a nonlinear way. Without these, even a very deep neural network with many layers would essentially just be doing linear calculations. It couldn't capture curvy, complex relationships in the data.
So the nonlinearity is the secret sauce for complexity.
It's absolutely crucial. It allows neural networks to approximate incredibly complex functions, learning intricate patterns in images, sound, and language that simpler models just can't handle.
Okay, that's powerful. What about language specifically? How does math help understand meaning?
A fascinating area is word embeddings, with techniques like word2vec. The core idea is to turn words into vectors, lists of numbers again, but in a special way.
How so?
These vectors live in a multi-dimensional space where the geometric distance between vectors actually reflects the semantic similarity or meaning difference between the words.
Wait, really? So cat and dog would have vectors that are closer together than cat and car?
Exactly, that's the goal. And it leads to almost magical results. You can do arithmetic with these word vectors to solve analogies.
Arithmetic with words.
Sort of. The classic example is take the vector for king, subtract the vector for man, and add the vector for woman. The resulting vector is often very close to the vector for queen.
Wow. Vector man plus vector woman. That's wild.
It is pretty mind-blowing. Now, the sources caution it doesn't always work perfectly. Sometimes the analogies it produces are a bit nonsensical, showing the limits. But it demonstrates how these mathematical representations can capture surprisingly deep relationships about language and the world just through patterns and numbers.
It really drives home that even these incredibly advanced systems are still built on these core math principles we've discussed. But surely it's not always perfect. AI makes mistakes, right? Especially with new data.
Absolutely. That brings us to a major challenge. Overfitting. This is a huge issue.
Overfitting sounds like it learned too well.
In a way, yes. It means the model learned the training data perfectly, maybe even memorizing the noise and specific quirks in that data, instead of learning the true underlying generalizable pattern.
So it aces the test, but fails in the real world.
Precisely. It performs brilliantly on the data it saw during training, but falls flat when shown new, unseen examples because it didn't learn the general concept.
Can you give an example?
Sure. Imagine training an AI to recognize cars, but you only show it pictures of, say, 10 specific models, all taken on sunny days. It might overfit and learn to recognize those specific models in sunshine. Show it a different model or the same model on a cloudy day, and it might fail.
Or the example from the sources about animals.
Right, the animal classification system that learned to associate animals with blurry backgrounds because that's how they often appeared in the training photos. It overfit to the background, not the animal itself. Show it an animal against a clear background, and it gets confused.
That's a tricky problem. How do you fight overfitting mathematically?
There are several techniques. One is regularization methods like L1 and L2. Essentially add a penalty to the model during training if its parameters, like W, get too large or complex. This encourages simpler, hopefully more generalizable models.
Kind of forces it to find simpler explanations.
Exactly. Another obvious, though not always possible, solution is just getting more diverse training data, more examples covering more situations.
Makes sense. More data, better generalization.
And there's also hyperparameter tuning. This isn't a direct math operation in the model, but it's the process of experimenting to find the best overall settings for the learning algorithm itself, things like the learning rate in gradient descent or the complexity controls. Finding the right hyperparameters helps balance learning the patterns without overfitting.
So it's a constant balancing act. And even with these techniques, as experts like Stuart Russell or Oren Etzioni point out, AI still struggles with things like genuine common sense, abstraction, or transferring knowledge easily between different tasks, right?
Definitely. Those are major frontiers. True generalization, common sense reasoning, transfer learning, these are areas where human intelligence still vastly outperforms current AI. There are deep challenges there.
But even with those challenges,
Right. Even with the challenges, the fundamental power comes back to that core ability we discussed. Using math, especially probability and pattern recognition through optimization, to find insights or make predictions from data, assigning a probability to an outcome, finding a subtle correlation that's the engine driving AI's usefulness today.
this has been incredibly insightful. It really feels like we've pulled back the curtain. Seeing how probability, patterns, optimization, these core mathematical ideas are behind so much of what AI does, from simple classification to complex language tasks, it really demystifies the magic.
Exactly. It's not about some unknowable consciousness. It's about the clever application of these mathematical tools to learn from data. And thinking about this, connecting it all maybe raises a final thought, a question for the future. Given that AI's power comes from finding patterns in data using math, what might be the next truly groundbreaking pattern that AI uncovers? Maybe a pattern so complex, so hidden in the data, that we humans, with our own cognitive limits, simply can't perceive it ourselves. What new understanding might that unlock?
Wow. That's a fascinating question to ponder. What patterns are out there that only math, wielded by AI, can reveal? Definitely something for you, our listeners, to think about. Keep observing how these mathematical foundations show up in the AI around you. Until next time, keep diving deep.